I'm going to draw a leaving group on it. Put iodine here. And this will be a secondary substrate that I'm interested in working with right now. And I'm going to draw this reaction something like this. And we're going to think about this particular reaction in the context of whether it's SN2 or SN1. So these are the only details of this. It's all we're given. Let's look at it and think about what might happen, why it might happen, or how we evaluate this particular reaction. Secondary substrate is a little bit tricky. Our substrate list is methyl, primary, secondary, tertiary. This is the best for SN2. This is the best for SN1. And indeed, this is impossible for SN2. And indeed, this is impossible for SN1. But these ones right here in the middle could be either. Particularly this semester, the secondary substrate could be either SN2 or SN1. And next week, secondary substrates will do a third reaction called elimination. But we're not there yet, and we're going to slowly get there so that when we do, you'll understand how to make that differentiation. So secondary substrates will be problematic, and when we see these, we have to look elsewhere. Well, the leaving group is written right here, and if it leaves as I minus, right? So the leaving group right now, it hasn't left yet, but when it leaves, it's I minus. And the leaving group matters for both SN2 and SN1, and this is a good leaving group for SN1 or SN2. Okay, so the leaving group gives us no clues. The substrate is not giving us any clues here. But all I've left you here with is this, which is the solvent. This is our solvent. And we have to characterize it as something. Apolar, nope, it has polar bonds, so it's polar. It has an OH bond, so it's protic. So this would be favored for SN1. It works in SN2, but we could say it's favored for SN1. And in this reaction, we don't have a nucleophile drawn, but we have lots of this. So we're going to assume that this plays the role of nucleophile as well. I could also write this, if I wanted to, this reaction. I could just write it simply as this being present here as well. But you should make this logical connection. And I'll try and put it together in the most compassionate way I can on our third exam, maybe writing it both times. So when you look at the equation, you know immediately substrate, leaving group, solvent, nucleophile. So I'll try to write it that way, whether it's SN2 or SN1, just to give you whatever fair advantage that I can think of. But right now, let's evaluate this as a nucleophile. Well, for SN1, all nucleophiles are equal. But let's try and rule it out for SN2. For SN2, this is a very poor nucleophile. For SN2, we have to think about nucleophile, and this is poor. And why would it be poor? Well, it's poor because it's electronegative atom, which is the antithesis of being a good nucleophile. Electronegativity is opposed to nucleophilicity. And it's neutral, so we have electronegative atom that really doesn't want to share its electrons with anything. But luckily, let's put this SN2 here. Luckily for SN1, doesn't matter. So this is how we'll bring together these concepts. So looking at this, again, substrate could go either way. This reaction could change completely if we added a good nucleophile like sulfur minus or carbon minus, maybe change the solvent to acetone, which is polar aprotic. So if we change the solvent in the nucleophile, maybe we can change the way this particular reaction takes place. In any event, we're definitely going to make a product by substitution here, but which mechanism it follows does matter. How we're going to draw that first arrow does matter. What are the stereochemical consequences of whether SN2 or SN1? These things do matter. So this reaction would be preferred to take place by SN1 because the solvent would be favored for SN1, and we have a very poor nucleophile for SN2. Well, that's not a problem for us for SN1. Right? This nucleophile is a poor nucleophile, but for SN1, it doesn't matter at all. Why don't you try and draw what you think the product would look like here, and let's just make one modification to the notes here for a minute. Let's actually just make this a chiral center here. So, sorry to do this to you, but let's just put a chiral center in right here. Okay, there's a hydrogen not drawn methyl group. Let's just put in a chiral center. And I want you to just draw in the two products we would get if we were using methanol, and all the other examples we were using water, HOH, and at the end we would be left with OH. But if we have CH3OH, what would the products we have here? Try and draw them in. There's two of them, both enantiomers of something, but what's the exact structure of these things? Just take a moment right now, draw it in, give me your best guess as what happens here. Again, try and draw your best guess at what the products would be here. The only thing I changed from previous slides was I replaced water with methanol. I'm hopeful that you could draw in methyl ether. This was one of the preview examples I gave, slightly different substrate. But this follows from our use of methanol in previous reactions as a solvent, like alkene addition reactions with acid. So I hope that you got these two products here drawn into your notes. And if you didn't, you can definitely practice this on your own as a mechanism. Make this group leave. You have a secondary carbocation. Add methanol to it. It will have oxonium ion, or an acidic proton here that we have to pluck off in the second acid-base step. And we'll get to these two products. We'll get to these two products because the carbocation is flat. P orbital is 50% up, 50% down. Methanol will have a 50% chance coming from top, 50% chance coming from the bottom. So this is a problem you could, on your own, try the mechanism, right? Give a detailed reaction mechanism that explains this experimental outcome. That's how I could ask this question. I could draw this whole thing here and say, give a detailed reaction mechanism that explains this stereochemical outcome. So there's ways to practice this. You should definitely practice these problems beyond just the way that I'm always presenting them to you. Okay, let's just look at one or two other facets about leaving groups, because we belabored that point in lecture yesterday when we were talking about converting bad leaving groups to good leaving groups. This was an issue we spent some time. This was an issue we spent some time with yesterday, converting a bad leaving group to a good leaving group. Recall for SN2, we spent most of our time with the alcohol functional group, and we reacted it with strong acid like HX. We made tosylates. There were two other conditions. We learned PBr3 or SOCl2, but these were the two important ones we learned yesterday. If you had strong acid to OH, converts it to water, which is a great leaving group. If we use tosyl chloride, we convert it to a tosylate ester, which then can be attacked. The same is true for SN1 reactions, but the leaving group matters. So again, let's look at OH, and let's look at tertiary butyl alcohol as our substrate. And let's imagine that we are trying to make tertiary butyl bromide from it, right? So let's imagine we're trying to make this particular conversion take place. Again, the mechanism has to be SN1. In the SN1 reaction mechanism, leaving group pops off first. If we try that right now, make tertiary carbocation, which is no problem, plus we see what the leaving group is, which is hydroxide, which is a impossible leaving group because it's a strong base. Right? So this is a strong base. This would be an impossible leaving group. It just simply will not leave because the leaving group matters equally for both of these reactions. Always have to be thinking about good leaving groups. So let's think about 1, 2, 3 possible methods to get this particular transformation to take place. Okay? Let's think about 3 possible methods. Maybe the method someone was thinking about trying here was sodium bromide. They just wanted to heat this thing up in sodium bromide. They were hoping hydroxide would pop off and Br- would attack, but this reaction simply doesn't work as written this way. So what are some strategies we could use here for this, right? Why don't you just supply me just short answers or reagents, whatever you want here. There's 2 or 3 ways we could get this to work. And it all focuses again on this converting a bad leaving group to a good leaving group. Let's use our knowledge from yesterday. Let's use our knowledge from yesterday to resolve this. So you guys just fill in some comments here privately if you're afraid to ask this reaction. Yeah, so give me a little more specifics on acid-base reaction. Give me a specific acid-base reagent you would want me to use here, right, to do this transformation. Okay. HBr is the right one, not HCl. HCl, I get it. You want acid-base reaction? Why not use HCl? Why not use HBr? Okay, because if we use HBr here, we'll protonate this first. This will leave as water. We'll practice it in a minute. And then we would have Br-, which would just attack to it. So HCl, fine, I get it. But specifically for this one, HBr would be good. If we wanted to convert this to chloride, HCl would be a good choice. So I appreciate that you wrote that. If we wanted to convert this from alcohol to iodide, HI would be a good choice. But Cl- or I- would be bad choices because we still have this problem here. We're not going to make strong bases a leaving group. Okay, other choices. Yeah, we could use tosylate, then what? Tosylate on its own isn't enough. We'd have to do tosylate, then what? So we could convert this to tosylate, but if our goal is to get it to bromide, what would we do after we first made it a... So we could react it first with tosyl chloride. The goal would be to make a tosylate. Right? So we use this reagent, tosyl chloride. This attacks sulfur, chloride leaves. We get a tosylate here. Then what would we use as a second step to put bromide in, right? Now we have a good leaving group. HBr is close, Jennifer, but why not just use sodium bromide at this point, right? Because if this is tosylate, then it's going to leave right away, and all we need is Br- to come in. So HBr is fine, but maybe there's some reasons we might see why not adding HBr everywhere is a good choice. So if we actually just convert it to a good leaving group, it'll leave. If we had Br-, it can just add right there. Okay, so HBr is not wrong, but sodium bromide would be the best. And the other choice is we could actually just take this reagent, PBr3, but again, this isn't really something for this particular semester for us to do, but this reagent is a complex series of steps which converts alcohols into bromides. But for us, the intellectual steps that you guys and girls were working out here, absolutely perfect. HBr or acid, right? Then tosylate, good, and then some sort of bromide source. So that's great. Thanks for just contributing a little bit how we could here. It's 10:05, and we're going to take just a quick break here because I wanted to end this particular portion of our notes and make a clear delineation in our notes. What we're going to finish off in today's lecture is a separate topic of carbocation rearrangements, which we do have time to discuss today. They were alluded to in our pre-lecture video. And I just want to make this